Hello everyone, it's July the 9th. Look at that, we have 9 notifications, and none of them concerns me, I think. Yep, nope. Alright, let's go right into it. Longest increasing subsequence. I have done this before. Yeah, I think I've done this before. Given an integer array, return the length of the longest strictly increasing subsequence that can be derived, so we can take anything out. It's a subsequence, yeah. Longest 2, 3, 7, 101. Yeah, I definitely done this before. And oof, but I don't remember. Can you come up with that runs in O1 login time? I don't remember. What did I do? Isn't that like trying to find the well, it's not peak. I mean, it's not mountain. We're not trying to find mountains, right? Because it's subsequence. It's not subarray. So I don't know, like 10, 9, 2, 5, 3, 7, 101, 18. I mean, I have to give you a hint. O and log n, right? So probably a heap. Yeah, I feel like I've done this before. Longest subsequence. I mean, let's go down to basics. Longest, shortest, most likely dynamic programming. Let's try dynamic programming. So let's say if at a certain index, right, we know the longest subsequence ending in the last one, right? We have a value, and then we'll look at the next one. If it is smaller, then we say it's going to be, oh, but we have to look ahead, look in the previous to find anything that is smaller than the current value. If we can find it, and then we will know, right? Which means if we can, right, if we can locate, yeah, so given a value, right, so given a current value, so like at each position, we know the longest subsequence that includes that value, right? So let's say 5. We know at 5, the longest increasing subsequence that ending at 5 or including 5 is 2, right? And then we'll look at 3. So in order to find, so the 3, what we can do is we look at the one ahead. If the head is smaller than me, then it's going to be this value plus 1. If the head is bigger than me, then I need to search through this in order to find a value that is just smaller than me. So mine will be this one plus 1. And this requires a search in the previous encountered values, right? To find where I am going to be. This can be solved. I mean, we've done this before, which is to keep a sorted array. Right? As you go through, you just keep it sorted, right? Just keep it sorted. Now we can use a sorted container, right? And then we just run a binary search in this, and then we know where this is, and we get the value out, right? And then once we get the value out, then this will be that plus 1, right? Or 1 just by itself. And then we take the larger one. So this one will be 2, right? So here is larger than this. Oh, but how about this? Huh. How about it? So like if I am larger than this, and I'm larger than every single one. But I need to find something that has the largest length, right? Largest length while the value is also smaller than me. So for this, I can basically pick all 3. But this is 2, so I can pick 2. So this one will be 3, right? And this will pick the largest one, so we'll give them 4, right? And this, yeah, I cannot just go to here. I need to find the largest. So for this one, I need to find the largest, which is this, which is 4, but I cannot do. So I need to find the next largest, which is this, and then I do. But this is not a but it does make sense. Like if 7 comes in, no, it doesn't actually. It doesn't make sense. What if like it's 10, 9, 5, 2, 3, right? If it's 10, 9, 5, 2, 3, and then we do binary search, we'll go to 5, and 5 only 1, right? But if we do 3, we're gonna get 2. So it's not binary search. It has to be a heap. But if it's a heap, if the top of the heap, right, the value is larger than me, then I need to put this one somewhere else. I need to put it somewhere else. So now we go back to 2 heaps. And we don't like 2 heaps, if I remember it right. We don't like 2 heaps. All right, we don't like 2 heaps. Now think about it again. If we have some value, right, that we already obtained the maximum overall, and we have some larger value later on, then we definitely can refer to this, right? Which means I actually don't need anything ahead of me. I just need myself. I just need this thing. Because the larger ones does not help. It might help, right? What if this one's small, like a 1, right? What if this is a 1? If this is a 1, and I say larger one doesn't help, I just stop popping out larger ones. And if we have something bigger, then the larger ones is gone. I think in your mind, right, in your mind as you go through everything, and you can push them into the heap, the longest will pop out, right? The longest pop out, and you check it. I mean, the thing is, if we have 2, so right here, right, 7 is 3, 101 is 4, 18, right? And then we pop this one out is 4, and we pop this one out, we know this one is 4. So when we have 2 values, right, we have 2 values which give us exactly the same length of longest increasing subsequence. When that happens, we always keep the small one because there's no point in keep the big one. If we have a big one, it can take this or take this. That will be fine. Which means, as we go through, right? As we go through, we eliminate the values, the big values that can give us the same result, right? So as we read, we push value in, like 10 in, and then 9, we pop it out, but as 10 is larger than me, and I would pop it out, and what we need to see, right, because this value is larger than me, right, so I cannot add to it. So this value, the length that this one represents is the biggest, right? Is the largest that I can achieve. And when I take it out, I need to compare, right? When I compare the next one, right? The next one, and the next one plus me, if I can achieve the same as this, then this one can be discarded, right? No problem. Which means we're just gonna run through this, pop the ones, like if we see one and it's bigger than me, and I pop save as someone else, pop save as someone else, and then until I find something that's large and smaller than me, then I push it in, then I have a value, right, what my value is. Then we go through the one that have been popped, right? And then we add back into the heap the ones that has a longer subsequence than me. If they don't, right, if they don't have a longer subsequence than me, then there's no point, right? And actually, when I pop it out, I just need to know, hold on. So we put them back only if adding my current value to the longer subsequence does not achieve the same as those larger ones. Therefore, if we can also keep a mapping of the current length, right? If we can keep a mapping of the current length, right? And 1, 2, 3, whatever, current length, and then the largest ending of the current length, not the largest and all the endings. But ideally, each should have only one ending, right? Should have one ending, which is the smallest. Right? We only have one ending, so we have a value here, right? One ending, and I look into it, right? I look into these endings, and I mean, if the top, right? Again, let's say if the top, the longest subsequence, the ending value is smaller than me, right? Now I push myself in, add 1, I get it, right? That's fine. If it's equal to me, then we don't consider, because it has to be strictly increasing. If the current top of the heap, the number is larger than me, right? If it's larger than me, then we need to look into the map, right? And to see, so we look into the map, right? We'll look into the map, and we'll go from large to small. We just keep going, and we say, because current number is larger than the top is larger than me, then I can get the top. So we have the top length. The top length is actually the longest length. We know it's the longest length. So what I need to know is whether the second longest length, and the value is, smaller than me. Is it smaller than me? All right, the second longest, whether it's smaller than me. If it is smaller than me, then we can pop the top and replace that one in. All right. If the second one is not smaller than me, then we keep searching. We keep going down the route. Right? We keep going until we find something that is right, that is, and basically what we're saying is one of the values will be smaller than me. So I can add in and I can plus 1, right? So we're going to go through this until we find one. We get the value, right? We see, oh, I'm larger than you. So we go through this until we find one that is smaller. The value is smaller than me. And then I'm going to plus 1, right? And then look in here and see if this one is the same size as I am. Right? And if it is larger than me, I replace it. If it is smaller than me, then I have no value, so I don't add myself to it. Okay, so, but how do I find? If you imagine, right, the num's length is 2500, so the total length is not going to be longer than 2500, right? It's not going to be longer than that. So if it's not going to be longer than that, I think this solution might actually work because the num is small. We can try it, right? But if we want to be even more precise, in this list, right, we can keep this list sorted. Right? We can keep this list sorted. And everything is unique in this list. So when we have a new value coming in, we just binary search it first so we know where to start. Right? We binary search first. So we binary search, we get to the value, right? We get to the value, and then we know the value, right? So we say that is where. So if I have a list, a sorted list, and we binary search, so I know who I am smaller to, who I'm immediately smaller to. So we have a bunch of value that I am smaller to, right? And then what I can do is I don't know what they represent, like they're. So we can, let's say we can go look into the length that they represent. Actually, no, we need to look at the one that's, but still we have to go, no, I don't think binary search is the right way to go. Like binary search will tell you which ones I'm smaller to, which one is larger to, right? So I can know exactly. But that won't help. I'm gonna stick to my first one, which actually I don't think is O and log n. I mean, because we have to go back. I probably don't have to go back too much. But I just want to know, like where. Like if I binary search it, right? Hold on. I think it is going to be ordered, right? The length, right? The length. Is it possible that we have a value, right? We have a number, say 10, give us a sequence of 3. is it possible that 9 gives us sequence 4? That's not possible, right? That's not possible. If 9 happens before 10, then 10 will have sequence of 5. If 9 happens after 10, and if 9 can get a sequence of 4, then 10 can get a sequence of 4 as well. That means the list that we're talking about is already sorted, right? It's already sorted. If it's already sorted, then we can go into the list, binary search, to get my position, right? My position who I'm bigger to, right? And that one, the one that I'm immediately bigger than, that one shall hold the highest, the longest subsequence length. So I'm comparing to that, like plus 1, right? And then comparing that to the one that's bigger than me, and if the one bigger than me has the same number of same length, then we swap it. So we keep this list, right? So this list indices will be the length, right? The indices will be the length, and the value of this list is the smallest number in the array that can achieve that length of subsequence, right? And every time we get a new one, we binary search it, and we see if we can swap, right? If we can swap. That is how I'm going to do it. And that will be O and log n. All right. So I have high confidence in this one. Yeah, I think it made sense. It made sense. No, I don't think I have done this before, but that's not the problem. So we're gonna say that's not res because that's called DP, right? So DP 0 position 0. We have to do this. Then for n, hold on. So we want to binary search it, which is fine for n in nums, right? So for each value coming out, we are going to binary search into DP, and I have the value, right? If I am the largest, yeah, so we're gonna say from bisect, import bisect right. So index equals bisect right DP and my current value. We say if index is equal to len DP, which means I am the largest than everybody else, then we do dp.append, right? dp.append n, right? Else it's a difficult sentence. Yeah, there is too possessive, too possessive, like nesting. All right, so index is smaller than we have the index is where I am supposed to be, and I do myself -1, right? Index -1. That's gonna be so like elif dp. We're also possible that, so we have to also consider elif index is 0. What if index is 0? Well, if index is 0 means I am the smallest, right? I am smaller. Oh, that's not possible because, oh, that is possible. This one shall not be 0. This one shall be math.infinite. Import math. Right? This has to be minus math.inf. then we can guarantee that this situation will not happen. This will not happen. So what I'm going to do is index minus 1, right? I'm going to say dp index minus 1 if this one is not equal to n. If it's equal to, then I don't consider. So if it's not equal to n, then my count, right? My count is going to be index. Index is my count, right? Index is my count. Then I'm going to compare myself to, so when I say if myself is smaller than dp index. If I'm smaller than dp index, then we say dp index shall equal to myself, right? I'm swapping. If it's larger, if I am not going to be larger than dp index because I did the binary search, right? I did the binary search, so I will always swap because I did a binary search, and I say it will always be the smallest. Every position will be the smallest number, right? The smallest number that can do it. And I do the binary search, and I'm going to add 1, then I will definitely be smaller than whatever that value is. So as long as it's not equal to, I think I can directly do it because I'm always going to be smaller than D. That's what binary search does. So I think I can always do this. All right. And then if it's equal, if I am equal to this, then there's nothing I need to do. And then that's it. Yeah, and then we're just going to return. What do we return? Length of dp. That's the longest sequence that we can get. All right, let's try and see if this one works. So we have this test case, and the result should be 4. And second test case, result is also 4. Last test case, that's a good test case. Result is 1. And I'm going to throw in a few, like this, right? This edge case. And I want to throw in one more, which is a decreasing, like 5, 4, 3, 2, 1. That should be 1 as well. All right, so we have these, and this is going to be nums, and this is going to be length of this nums. Try it. And it's not correct at all. That is not correct at all. 0, 1, 2. We end badly here, and we're missing a 1. All right, let's figure out something is not right. That's fine. So every time coming in, I do a bunch of this, and I'm just going to check what does my DP look like. Right? What does my DP look like? All right, let's see. So 10, 9, 2, 2, 5, 2, 3, 2, 3, 7, 2, 3, 7, this, 2, 3, that's correct, which means 0, 1, 1, 2, 3, 4, 5, or the length of dp minus 1. Then I think I can get most of them pass except for one of them. So we need to take care of this one. All right, so this one is very peculiar. If I keep adding, I say, I think I know why. Because of, so I need to see Minus 1 is equal to n. Okay, so no, so it's going to be this. If this is not equal to n, if it's smaller or equal to n, then we do this. Else, no. If this one is alright, so if it's not equal to n, right, and then when they say if index is equal to len dp. If equal to len dp, then dp dot append n. Otherwise, right? Which I think, yeah, this one shall be right. There you go. All right, they're all passed. Let's see if we can make it shorter. Is it possible? It is not equal to n. It's equal to n, we just don't do anything. If it's not equal to n, we're gonna check. Right, this is a new one, so we append. Otherwise, we swap. Yes, that's easy enough. That's easy enough. Yeah. We have to import bisect. I don't know. I'll run the code first. Yep. Try it. Pending. Accepted. Nice. So that is O1 login. I think we'll have very good runtime on this one. Exactly. Very good runtime. So how do I explain this? So the goal, right? The goal is to record, right? To record the smallest value in nums, that can yield any length of LIS, right? Any length of LIS. We can keep these smallest values in an array with the array index being the length of LIS corresponding to each value. Smallest value in nums, that is the end of any length of this, right? With the array indices. Index being the length of the LIS corresponding to each value. Since this array must also be sorted, this can be proved like this. Suppose, right, we can prove it. Suppose we have 9, we have dp, let's say dp4 equals 9 and dp 3 equals 10, right? Which means 9 is the end, is the smallest end to an LIS of length 4, whereas 10 is the smallest and to an LIS of length 3. This is not possible because if 10 occurs in, if 10 occurs, is not possible because if 10 occurs after 9, then 10 shall have, then we shall have, then we shall have dp 5 equals 10. If 10 occurs before 9, then we shall have dp 3 equals 9, right? Therefore, the dp array must be sorted, right? We can binary search binary search this array to find where the current value is going to be located. Then, if the current value is largest, I mean, we can even save one dp run, right? We can just check, and just check if it is larger, then we add. If it's not larger, maybe we can squeeze out a few more performance. If the current value is the largest, we simply append it to the end. Otherwise, we replace, right? We replace the value, in dp that is just larger than the current value, because the current value can achieve, right? The current value can achieve the same LIS length as the value just larger. Yeah, which is just larger. If the current value is a repeat, then we discard it. So it runs in O(n log n. Right, runs in O(n log n. But I'm not going to report because I think we might be able to do better. So we can just say if n is larger than dp minus 1, right? Then we immediately just say dp.append n. Else, then we do binary search, and we know it's not at the end, right? It's not at the end, it's not, and then we just can say if this, then we do this, right? So I just swapped it around. I think it shall be performing slightly better because we only do binary search when we're sure that the current value is not the largest. Right? And we basically make it easier to handle as well. So we're gonna go, I might have a solution for this one. Yep, does have a solution. And I also can see like if I've done this before. Oh, I've done this many, many times. Like literally many, many times. Oh wow, there is a much better way. My way is not the best. Hold on, let's try this one. So this one's faster. This one's slightly faster, 92 milliseconds, but still cannot compare to 36, right? Does not compare to 36. So this one give us, I'm gonna record 92. milliseconds, or 78% ranking. Well, we've done this, pounded on this one many times. The first time we've done this is January the 10th, 2019. And I was writing Java. And then I couldn't solve it. Oh, I did solve it eventually, right? But I don't like it probably. So the next day, January 11th, 2019, I kept solving it. Oh wow, it lasted a long time. And so that's the first round when I did it. Second round was October 30th, 2020. That's just last year. Have I started recording back then? I don't remember. And my first answer is 3,552 milliseconds. That's pretty bad. We optimized it, gets better, and finally, all right, let's take a look. What do we have this? I don't remember. It's super duper fast. Binary, yeah. If n is equal to, continue. If it's this, else, and then len. Oh. It's the same. It's exactly the same solution. Exactly the same solution. They might have changed the test case or whatnot, but yep, we got this one on our own. So I see this as improvement, right? It's definitely improvement, because in the past I wasn't able to figure out this solution. I think I definitely look at the answer. And this is the same, and because we drilled in it ourselves through the analysis, we have a better understanding of what we're actually doing. And actually, because we have the history, I think we can take a look. I think we started, yeah, see, 2020, October, so let's see, October 30th. So we can just put it out, 2020, and no, 10, 30, yeah, that's the one. Hold on, I'm gonna do it not side by side, but just here, right? So this is the exact same problem. All right, back then, I said very tough for me. Whatever I was saying, I got 27% ranking. And so it's O(n) squared, right? It's O(n) squared. I mean, O(n) squared works because there's only 2,500, right? And oh, what is this solution? What is this? Have a merge, have in. Wait, what? Segment. I was using segment tree. How? Oh my god. All right. This must be following some of the solutions, but no. Segment tree, no. Okay, so oh, I don't have two solutions. Wait, did I not take a look at the O(n) login? Or maybe segment tree is O(n) login. Let's see. Let's see how fast did I do. I think this is not a segment tree. This probably is a segment tree solution. No. This is the optimized. No, that's another one I was looking for. And I know this one's not segment tree. Which one is segment tree? Did I not even run it? No, this is just plain old. It's like different. Like the one I submitted is different from the. Like what the hell? Huh. I don't know. runtime error. Which one? This one. Where is the hash solution? Did I not commit the code? Alright, that's weird. That's very weird. I labeled this, but I didn't really code it in here. Did I even... What's this one? Wrong answer. Oh, I was trying the binary search. Oh, look at the test. It's 24 back then. Right now, we have 54. So added 30 test cases. That's why. Alright, anyway. Let's take a look at the solution. Who used a segment tree to do this? The hell? And I vaguely remember this, dynamically creating segment tree. So what's the logic behind? Query. Have a key. And 0, 1. So root is the minimum value. And I'm actually trying to figure out what this one is, the one I wrote in the past. It's so complicated. Alright, so root is going to be a segment tree node, right? And then for each one in them, we're going to say length and count. We're going to query the current root. So we query the root given n minus 1. Oh, why n minus 1? And I insert. Did I have an insert? I have insert root n and then length plus 1 and count. And we return the value. So I think what I'm saying is, I don't know what I'm saying. Okay, value, what's our right, left, right, middle? Okay, that's a range. Range left, range right. And these are the trees. And I use property. I don't remember what property is. So the property left is going to be either itself or seg node this. Okay, so that means is if if this is none, but why would this one be none? Because it will always be something, right? Algorithm times out due to creating the entire segment tree. Merge to length and count of adjacent range. The length is ls from the beginning of the input numbers to some number within the range denoted by the node that holds, well, typo, holds the tuple. Length is not the length of else contained within the range denoted by the node. For a range 3, 6, if the length is 6, that means ls starting from the beginning of the numbers, which apparently is outside the range, and ending in range. Ending in the range. So we start at the beginning, we ending in this range. Okay, so now we say we start, right? We're gonna start. So this is the value, value what's the value? The length and count. What's length? Length is LIS. Till some number within the range denoted by the node. How about count? What's count? If the length is 6, that means I know what it's trying to say, okay? So I want to merge two things. We say if 0 is the same, which means the length is the same. Then if the length is the same, I think the range isn't the range. Don't know. I don't know, honestly. Who calls merge? Here we calls merge. A merge result is the query. Oh, this is a recursion. Oh man, did I write this? What the hell? Value and value. So merge the value into the node. Okay. So we say if the count is the same, right? Because the length is the same. Then we say count. I don't know what count is. I need to explain. Then return. Oh, I'm trying to merge two range, right? And I still don't know what the hell is count. The number of values? I guess it's the number of values, right? The number of values in this range. So if I want to merge two, right? If I want to merge the two, so we say if they are length is the same, then after the merge, the length will be the same, but the count will increase. If v1 is 0, so if that means if it's not 0, right? If it's 0, then we just return 0. So if we merge the two, otherwise we take the max, right? So we have two range, and we want to merge the two range, and we just take the max v1 and v2. I'll be comparing the length, right? I'm just comparing the length. Yeah, that's true. We have a range, okay. Insert a value, which is the length and count of LIS that ends with key into the given node. So I have a node, I have a key. We say if node right range left, so as the leaf node, then no value. We're gonna merge merge this value with my node value. This just give me. I still don't know why we need count. I didn't see the count being used. I say if the node right medium is larger than key, so insert node.left key value, otherwise insert node.right key. After we finish, then we merge the current value. Yeah, that's that. On query, length and count of LIS within the range, right? So we have a range. If this, I return node.value, yeah. If right range left is larger than key, hold on. If range right. If range right is actually the value is smaller than my current key, then I return no dot value. That's true. If range left is larger than key, so I'm smaller than the range left, then I return this true. Otherwise, I need to query the left with a key, and then query the right with a key. Yeah, because the key is in the middle, right? So I'm going to query left, query right, and I have to query when to merge them. And the root is this, and for each one, we're going to query n minus 1, right? So we query n minus 1, so the one smaller than me, so we get the length and count. Yeah, I don't see the count being used in the entire algorithm. And then after we query it, so we know, now we're going to insert into the root with my current value, that's the key. Then insert as the key. And the value is going to be length plus 1 and count. I think we can remove count. I don't even know what count is. And oh, count is used here. Then what is length? Huh? Wait, what? Alright, screw this. It's just for fun, but damn. Why did I torture myself like that? Alright. Dynamic programming. Let's just kind of go through, see if 2. Hold on. 9, ignore it. Since 5 larger than 2, building our subsequent ending at 2, set dp3 equals max, dp3, dp2 plus 1. Yeah, 3, 10, ignore, 9, ignore, 2, we can add, 3, ignore, 7. Yeah, that's exactly the way that we are thinking. So 7, we can update it once, 5, update it twice. Not just 7. Okay, so return the max. Yep. So on squared, right? On squared. Intelligently build a subsequence. On squared. Yeah. And then improve a binary search. Yep. I don't. Oh, bisect left. Yeah, bisect left can do this. Yep, pretty good. Pretty good. I think I was following this BIT. Binary index tree. Yeah, you can call this the max value m and is smaller is the number of elements. Increase base. All right, let's see the BIT. I don't want to write a segment tree myself in my life because BIT can solve, I think, from my understanding, can solve all the segment tree problem. Okay, so since this, we can convert numbers to 1 to this, and store into the BIT. We build max binary index tree. two operators get return the maximum value of indices in range 1 to maximum value. Okay, update a value into bit index. Enter numbers. So numbers for this range, right? And then longest ls equals .get nums. That's the indices. That's the index. The longest. Hold on. What we're trying to do? What are we trying to do? What we're trying to do. So we have a range, right? The range is from 1 to the largest value, right? From 1 to the largest value. That is our range. And that is our range. So what we're trying to do is, given a current value, right? Given a current value, and we say in a different range, any range will give us a maximum LIS, right? So what we're trying to see is, given nums I minus 1, right? Want to find the longest subsequence to that. So now I can update this. Yes. The answer is to get maximum of all values. Nice. I think I got it. Lens, base. Let's try it. I mean, we have BIT prepared, right? We have BIT prepared. I mean, try to. I mean, you do it yourself. You kind of understand, right? So, what we're gonna do. So I'm gonna open the BIT. I think it's in useful. So it's a useful BIT. Yeah. Copy and paste the entire thing. Probably should also read it again. But anyway, so that's the BIT, right? So the BIT initialize 1 based, and update 1 larger. So update position by adding delta. By adding delta. So at this position, we need to add delta. So add 1, right? No, not add. Add what? Add delta. So we know the previous one, right? And the current one, we need to add it. I mean, we have this. I think we just get it out. So with smaller than this, a bit this plus equal to this, and I goes to the next one. I goes to the next one. Query sum of values in the range 0 to max R. Sum of the values. So it's slightly different, right? It's slightly different. We don't query. So the query, we're gonna add everything, right? We're gonna add everything, but what do we want? We want, when we query this, to give us the largest, this point, right? And then we query this, so we know a current, we have to add, hold on. Hold a sec. For each value, we have a range. And now I don't understand. Because if we're talking about range, doesn't that mean the order doesn't matter anymore? From the start to the current value minus 1, right? We're saying, but that's the order that when we push it in, right? And then we're just going to add that value. Every time we do it, we're going to add current value to it, to the range, right? So when given a new value, so we're going to query it. But we're not, are we adding the values together? Yeah, I think we are adding the values together, which is the number smaller than this, the number smaller than in this range, smaller than this range. So we add them together is the range sum, right? The range sum. Yeah, so the total number, right? But that's the total number. But what should I update? What should I update? I shall update. So like I know, so if I'm given 10, I know 9 will give me a certain number, right? 9 will give me a certain LLS. So I know 10 is going to be that value plus 1, right? So I push that to everything. What if I encounter 10 again? Don't I have to keep check, like I don't duplicate? Because if I duplicate, then what's the point, right? I cannot duplicate. I can obtain, I can query it, right? I can query it. We push the value in, right? Every value comes up, we push the value in, and I have to read through if the value is duplicate. Well, I can check to see if the value is 0. If the value is 0, then it's a duplicate. If it's not 0, then we don't worry. And like it's a duplicate, then we don't do it. So position delta max range. Okay, so we're gonna do n gonna equal to 2 times 10 to the 4th plus 1. That is the range, right? Yeah, that is the range. So when say bit equals bit n, and then what we're gonna say is for each value, right? For n in nums, and each value we're going to give it a every value is 0, right? So for each value we are going to look for the first value, we're going to return 0. So we're going to say previous length equal to bit dot query, right? Max range is to be n minus 1, right? N minus 1. And then after that, I'm going to say bit dot update position. Position going to be n, right? And delta going to be pre-length plus 1. But of course, there's a base, so we have to define a base as well. A base is 10 to the 4th plus 1. Should I plus 1 or should I not plus 1? 10 to the 4th. So if 10 to the 4th is 0 to, yeah, I think base is just 10 to the 4th. Yeah, base is 10 to the 4th. So every time is going to be plus base. And here is an update, this plus base, right? But basically, we use BIT to quickly find out, right, on a query, we'll quickly find out at every value possible, right, what is the longest subsequence ending like that. So we just give the longest subsequence and then we do this. Once we finish, we're just going to return bit dot query, right, and the query n, the largest value. Can we even query n? Yeah, I think we, hold on, I think the one base, I handle the one base here, so this has to be the total length. Total length, yeah, I think it's fine. Total length, so we're going to say it's going to be from 0 to 10 to the 4th, right? 0 to 10 to the 4th. It's 0 to 2 times 10 to the 4th, which the length is this. Let's give it a shot. I'm not very confident though. Query missing. So query hold on. Query missing 1 required. Oh, I think I made the same mistake in the past. It's BIT. List out of range. What does that mean? That means, I think it's the last one. I'm going to query it. Yeah, I think this is wrong. This should be 2 times base. Nope. That is not correct. Nope. Hold on. What are we doing here? So we have a range, right? And then each number, we want to know yeah, what I'm very iffy about is this, the query. So the query gives us the sum of everything. Do we want the sum of everything? I don't think we want the sum of everything. The sum of everything, because this is we do a query sum, right? So with a prefix sum, we need to add them together to get a sum. But what we want, if we have a value corresponding to each index, right? Corresponding to each index, and that is, let's say, the LIS ending there, right? And if we get a new one, and when we insert, right, it's going to be update to that specific value. I think it's to that specific value, right? It's to that specific value. And to that specific value and everybody below it, right? Everybody below it. But shouldn't we like just update? Hold on. Let me think again. Let me think again. Update. Shouldn't it just be 1? So we query this, right? We query this. Now I get the value and I update. And everybody gonna be add to that. And I query again. I think what we need to do is we query this, right? And then what we need to update is this, but that's not a value. I think it's this value minus bit dot, so bit dot bit dot bit dot bit, so bit dot bit n plus base plus 1, right? So it should be like this. We update. This is what we update. Like if it's 0, otherwise it needs to be 0, right? So we update that, and let's try this one. Still not correct. Well, it's not correct because the query. I think it's because the query. Hold on. When I update, right? When I update everybody. But when I query, I think it's the query. Maybe the query is just to get out the value itself. Hold on. Because there's no sum, right? You don't add them together. So I can just return self.bit I. What if we just do that? No, that's that ain't correct. That ain't correct. Huh. Because when I update, all right, let's do this. Let's smaller values. It's easier to understand. Oh, no, it's I can't print out. It's too big. It's way too big. What are we doing here? What we want is when we query, it gives us the total number, right? The total number of LS in this whole range, which means each value what's going to give us is just within whatever range. Right? Within that range, what's the LIS? And within this range, what's the LIS? And we add them together. Okay, so if that's the case, we do have to do this, right? I think the problem is, like, if we do this, tell us the result is 6. And we can actually, like, instead of doing this, right, we can say n equals, what's the largest value? The largest value is 4, n equals 4, right? And base is going to be no base. Oh, it's different. Oh, because it's 2 times base. to the base of 1. Oh, 2 times base. Doesn't matter. It's not 2 times base. It's going to be the largest value. The largest value is 3. Right? Yep. So now we can kind of take a look. So let's print bit.bit. What does this mean? This means if it's 1 based, right? 1, 2, 3, 4. 1, 2, 3, 4, right? And we say, actually, print this and print freeline and also print n. Oh, m minus 1 plus base. Hold on. Yeah, it's fine. It's fine. So what we need is to make it 0, like 0 based, and this can handle the plus 1. So it just needs to be 0. That is 0. n minus 1 plus. That is not 0. That is not 0. No, this one is not 0. So to make it 0, the base. So we need to do n minus 1. So let's shift it. Let's do base is 1, right? If base is 1 and n doesn't change, so whatever value we get out, we add a base. And then we have index out of range. And here, which means now the base is the smallest. The base is the value. Then when you add, it's going to give you the smallest. So base is 0. It is 0. Yeah, this is right. We just need to take a look. So when the current is 0, pre-len is 0. Now we update. That's update 0, pre-len 1. So after update, we have this, which means 1 based, right? So what we're looking at, so we have is 0, 1, 2, 3. So we ignore the first one. So 0 is 1. 1 is 1. 2, 3 is 1. Which means if I want to, what does this mean? This means I don't know what this means. Shall be 4. 0, 1, 2, 3, right? It shall be 4. If each one, let's say from start to here, that's not correct, right? So this is 2, right? So 1. What is the, if I say I start from here, that's 1. Start from here, that's also 1. That is correct. And then we go 1, and the 1 coming in, this becomes 2. This is also 2, right? And we just say if we start from 3, we have 2, right? And then 0 comes in again. We don't really change anything. And now 3 comes in. Right, 3 comes in. Then this one adds 1 more to it. Which means from 3 counting down is 3. Now 2 comes in. 2 comes in, we need to add, so we say it's 3, right? 3 plus 1. And we add 3 because the prelen is 2. Because query this, the prelen is 2. So plus 1 is going to be 3. Which is true, this should be 3. But this is now 6. Right? This shall not be 6. We add 3. This should just only add 1. Because this is at 1. Right? We're adding 1. Try to think about it again. We use query. That's the prelen plus 1 minus bit. That means that's the amount that I can get by being present, right? If I'm present, then I say I'm going to add this value, then everybody else has to add the same value. But what is this is everybody else should not be adding at the same value. All right, I need to check. All right, let's come bit again. Let's see the get, which is query. Okay, this is different. Update is also different. So we're not adding, we're taking the max. We're taking the max. That is true. Hold on, what are we doing? Return the max value of index. What he's saying is, hold on. At each index, what we're saving is the longest LIS. Alright, the longest LIS that ending from the start to ending here. Alright, and then we query it. So when we query, it's the longest LIS. After we query it, we'll get a new one. Now we're going to update it, right? And we update it, so everybody gets updated with the new longest from myself up to the. That is correct. So I need to change. So this is not plus equal to delta, right? It's gonna be a maximum self.bit I and delta, right? The maximum self.bit I and delta. So we always keep the maximum, and then res equals also maximum res and this. So this will give us the maximum, right? So, and then we can start There's a total number, n is the total number, and a base is the value that can get a base to 0, right? And bit equals bit. For each one, we get a pre-length, and I'm going to update just +1. And we're going to query the largest value, which is going to be 2 times base. And we pass. Nice. The IT solution following this. This is not a prefix sum bit, but a prefix max bit. Each query returns the longest LIS ending in a given value, right? Longest LIS ending a given value, and starting with min value, right? Each query returns the longest LIS ending in a given value. That's true. And given value. This way, we can obtain the LIS, the length of LIS of current value -1, and derive the longest LIS of the current value. Yeah, I was having problem. Right? I was having issue figuring out the logic inside bit. I thought we will keep the longest LIS of each segment, in each segment, but this is not right. Each segment, which will then require addition, right? Addition when doing query and update, but this is not correct. This is not correct because each because each index shall hold the longest LIS directly. Hence, there is no addition. Yeah. Each one holds the longest because that's the segment tree. What segment tree does is it returns one value, right? It turns one value, and it can be a sum, right? That's one value. We just add everybody together, or it could be a min or max of a range, right? The sum of a range. Remember, just keep in mind, BIT or segment tree obtains, right? It obtains the sum, min, or max of a range. Right? In our case, we shall get the max of a range, right? So the maximum of this range, and then we get every single one, and then we get a maximum of this. Yeah, that is the way to go. Okay, we're gonna submit this as well. Yeah, very, very good. BIT. Yeah, I need to get more comfortable with BIT. BIT is really, really useful, it feels like. It's the same as Union Find, right? It's just very useful. Let's see how fast this one runs. Mediocre, right? Mediocre. Because we can definitely make it better by, I think, we can get a min max, right? We can get min max equals min n, min nums, and max nums. Maybe it'll be faster. So this is just going to be max minus min plus 1, and base is just going to be min. Right? And we can run it. Oh, that is not correct. Oh, it's not. This is max plus 1. No, it's not max plus 1. It's max minus min. Yeah, it's gonna be max minus min and 0 plus 1. Still not right. Oh, the base has to be min this. Oh, because this query, so the query needs to be max, right? Oh no, max. Query needs to be max. There we go. So we use this. Maybe we can shrink the time a little bit. Let's see. So this. Can we shrink the time? 292. Runtime error. Ah, we have the negative value. Nope. It's not the. Yeah. No, I don't like it. I don't like it. No me gusta. We just get the maximum range, which is fine, right? Which is fine. Yeah, this is fine. Yeah, we just leave like this. It's fine. All right, that's it. 2 solutions. One is dynamic programming with binary search, and the other is segment tree. I mean, it's always good, right, to try segment tree. Just help you understand. But I think it still take some time. Take a few more practice on segment tree for me to understand how to use it efficiently. All right, that's it. That's it for today. See you guys tomorrow. Adios.